Here I discussed a few ways that we will describe fluid motion in advanced fluid dynamics. So the full description of the fluid motion is given by the velocity field. Remember that the velocity field is one of the two fields that we will usually look at in IFD, the other one being the pressure field. So the velocity field is known when we know the flow velocity u at every single position in the flow field, so x being here the position vector. So at every single position vector, but also at every given time. When the flow changes with time, so when the velocity field does depend directly on time, we say that the flow is unsteady. The flow and when the flow is independent on time, so it does not change with time, the flow is said to be steady, or you will also hear stationary. So there are a few flow fields that as we go with the class you will see more and more, and the simplest ones we can discuss here already. So the kinematics of the simplest flow we can discuss. One is the solid body rotation, for example. So here is how the velocity field associated with the solid body rotation looks like. So this is a velocity field. So at every single x and y location there is a vector associated, which is which corresponds to the flow velocity. This flow field can be expressed in Cartesian coordinate, for example. The velocity here is a function of the 2D position vector. It is a steady flow, and that's because it is independent on time here. And it has two components, one in the x, one in the y direction. And the component along the x direction is minus omega y, and the component along the x position, the y direction, is omega x. Here omega is the angular rotation velocity. So the angular velocity. You could also express this velocity field in polar coordinates, where u would be a function of the position vector, in that case the radial and circumferential coordinates. In that case we need to give the component along the radial direction and the component along the circumferential direction. Now note, of course, if we have a solid body rotation, then at every given point here there is no component of the velocity in the radial direction, and there is only a component of the velocity in the circumferential direction. So the component in the radial direction ur is equal to 0. The component in the circumferential direction, so normal or perpendicular to the radial direction, is non-zero, and it's increasing linearly with the distance to the origin. So here it's 0 and increases linearly with r. And the coefficient of proportionality, of course, is the rotation, the angular velocity. So the component in the circumferential direction is omega r. Another flow field that we will see a lot is the irrotational vortex. Here is what the velocity field looks like. This flow is quite easy to recognize because, again, if you look at the flow velocity, so this is the vector field, again at every single point we can define the flow velocity vector. We see that, again, there is no component of the velocity field in the radial direction, so the flow is turning around, if you want, but now the magnitude of the velocity field is not increasing with r, but it is decreasing with r, and in fact it is decreasing in 1 over r. So the coordinates, the components, of the velocity field of the irrotational vortex in polar coordinates would be, so there would be no component in the radial direction, that would be 0, and in the circumferential direction it will scale in 1 over r, and usually we will write the coefficient as gamma over 2 pi, and as we'll discuss later on in the class, in the second quarter, gamma here is called the circulation. So gamma divided by 2 pi is a constant, and gamma is called the circulation. Okay, so this is a straightforward introduction of what velocity fields are. As you will see in the class, we will also often describe fluid motion with streamlines. So the streamlines provide an instantaneous snapshot of where the flow is going. So streamlines are always constructed from the velocity field at a given time t, and the streamlines then corresponds to a curve which is everywhere tangent to the local velocity field, to the local velocity vector. So here is a first example. Let's consider the flow around the cylinder. This flow we'll discuss more in detail in the second quarter. The velocity field corresponds to the ideal flow around a cylinder. The blue arrows here represent the velocity field, and as you can, and the red arrows here, they are the red lines, the red curves, they are streamlines, and as you can see at every single point here, the streamline is tangent to the local velocity field. So here the velocity field is horizontal and the streamline has an horizontal tangent, and here you can see it well here, for example, the streamline is tangent to the local velocity field. Now if you look at the previous flows we've looked before, so the streamlines here of an irrotational vortex, just think what curve would be always tangent to the local velocity vector, and you get the idea. You see here that the streamlines of the rotational vortex would be circles. Same for the solid body rotation.